interesting part. Somehow what I have described so far, except for the theorem last time, was the situation like 2 years ago, okay? And I mean, when we are doing the computation of the action on this adel class space, which is the quotient of the adel by k cross, okay, in fact, when I was doing the computation and writing the trace formula as a sum, so if you want, as a sum over all places of the integral over the local field of h of u inverse over the modulus 1 minus u d star u. Okay, when we were writing this formula, in fact, I mean, there are lots of points which are quite tricky about this formula, and one of them was the following. Remember that we were looking at the periodic orbits of the action of the adel class group, so of ck, acting on x. Now, when you look, as I said last time, just at the end, you find out that you look at the fixed points. So you look at the equation like an adel class j multiplied by an adel class is equal to the adel class. And you quickly find out that unless xv vanishes for some place, I mean, the only j's which will fulfill this condition are the identity. Okay? Now, this tells you, if you want, that the set of points which contribute is a union of the hyperplanes, say h sub v, which are labeled by the places. Okay, and for each of these hyperplanes, you can convince yourself that each of them is like the closure of a periodic orbit. But because the space is a very tricky space, okay, you have to be over careful. And in fact, I mean, obviously you could impose two conditions. I mean, you could have two places, like v1 and v2, where xv1 is equal to 0 and xv2 is equal to 0, okay? And so you have these all stratas, if you want, of points which are more and more fixed, essentially. And you also have the point where xv is equal to 0 for all v, namely the point x equals 0. That's certainly a fixed point, okay, for the action. I mean, it's fixed by the whole group. So, I mean, the formula which I have written here is very problematic at first when you see that. Now, the explanation that I had in the content note was extremely rough. The explanation was that, you see, if you consider the isotropy of the set of points where, say, two different places vanish, something like that, and when you look at the corresponding isotropy, you'll find it's not closed. Okay? Now, when you consider the point where x is equal to 0, what is really going on is that the point 0 is not a point, it is an orbifold point. Because remember that the adel class space is divided by k cross. Now, if you consider the adel which is 0, this point has a big isotropy, which is k star itself. Okay? So it's a little bit, if you want, when you consider the quotient of a manifold by a group, and when you have a fixed point for that discrete group. So it's an orbifold point. So in other words, what I was arguing about, but only very, very qualitatively, is that none of this should contribute. 0 should not contribute because it is divided by an infinite group, okay? And these multiple fixed points, I mean, should not contribute because, say, they are in the closure of one of them, or because of this. But of course, this was, absolutely unconvincing, okay? So, I mean, it was absolutely necessary to make things rigorous. And you will notice that exactly the same problems occur already at the level of finitely many places. So this is the right thing to do, of course. Namely, to consider finitely many places at a time. I will explain then why. If you have that, you know what is going on in general. So let's consider S, which is a finite set of places, but which contains all the places V which divide infinity, all the infinite places. Okay, I mean, the reason why we want to contain all the infinite places is that, after all, there are only finitely many infinite places. Okay, and moreover, I mean, the nice theorems like the Dirichlet unit theorem and so on will be available, provided we enclose all the infinite places. Right? So now, what I will explain what is the corresponding sort of finite situation when you consider finitely many places. We shall see immediately that the same problems occur. Namely, the problems of many places where the coordinate vanishes or the point 0 and so on. Okay, and there we shall be really able to compute and to see why they don't contribute concretely. Okay, but this will be quite hard. It will be much harder than what I did last time. Okay, so what is the situation? All right, what is the situation if I have a finite set of places? Well, then you see the space of adel classes. First of all, sorry, the adel class group can be localized if you want. And it's replaced by the following. It is replaced by the quotient, so of the what replaces the adels, namely which is the product of the multiplicative groups for V only in this finite set of places. This is already quite a big group. And it is divided by a discrete subgroup, which is a group of S units, which I will denote by OS star. Okay, and the group of S units replaces, if you want, K cross, the invertible elements in the field. And is defined like this: OS star is a subgroup of K cross, so it is the set of elements Q which are in K star, K cross, and satisfies the following condition that if you look at QL in absolute value, it has to be equal to 1 for any place L which does not belong to the finite set S. Okay? Now remember that S was containing all infinite places. So that condition, for instance, if we would take exactly the complement of infinite places, that condition would mean that Q is a unit. Namely, it has to be an integer, okay, because the norm of QL is less than 1 for any L not belonging to S, and its inverse has to be an integer, because the same condition is true for Q inverse. Okay, so if we would take S to be the set of infinite places, that would be the units. And in general, these are called the S units. Now, it is a variant of the Dirichlet unit theorem that if you look at this group OS star, so OS star is in fact discrete and co-compact. Discrete and co-compact. In the group, this group I will call C, in the following group, J sub S, where J sub S sub 1 is the following. You see, it is a set of elements J of norm 1, J equals 1, in the following group, which is just the product of the K star V. And sometimes I will denote this product by J sub S. Okay? So of course, I mean, this replaces the group of adels. This replaces the group of adels of modulus 1. Okay? And the Dirichlet units theorem is telling you that, this group of S units is discrete and co-compact in the group of adels of modulus 1. Problem?
The product over V is...
V in S, of course, yes. Always V in S.
But the matter in contraction is
yes.
Q absolute value L. The L is absolute value rather than Q. When you define OS star, you have elements in the field K star, and you look at the various absolute values.
Not in S. Not in S.
Or L different from X.
That's the notation.
L.
Yeah.
You can also write it like
You can embed everything.
Sure, but I mean, for me, it's the same. I mean, this is the same for me. I mean, this is the same as Q sub R. Yeah, sure, that's the same.
Yeah.
Okay, I mean, I identify Q with the adel, which is equal to Q anywhere. Okay, fine. All right. So I mean, So this is quite a nice group, and so on. It replaces the adel class group, of course, this quotient, and it has this proper map, which is a module, which maps to R plus star. Okay, proper with co-compact range and so on, as usual. So it has exactly the same properties as the adel class group. In fact, it's very close to the adel class group as soon as you take a sufficiently large set of places. Okay, it's almost the same thing. It differs from it by a very compact and small piece. Right. So by what is replaced the adel class space? So this is what is really important. So the adel class space now is replaced by the following space, which is X sub S. So X sub S is just the quotient of now, of course, the product of the field for V in S divided by OS star. Okay, and we shall have to get acquainted with this space. What does it look like? So let's look at this space. I mean, it's obvious that all of what I said before, namely that the adel class group is acting on the adel class space and so on, I mean, all of this goes through. There is absolutely no difference. Okay? But let's get familiar with this space. So let's look at some examples. Okay, let me take two very simple examples. So let's take some examples let's first take k equals q of square root of 2, and let's take S to be the infinite places. Of course, there are two infinite places, okay, for this field. So the what is the S units? They are the units of the field, okay? And the units of the field, there are things like 1 plus square root of 2, for instance, okay, to the power n, for instance, or things of this type, 1 plus square root of 2, it's a unit because it's an element, it's an integer, okay, and it has an inverse which is square root of 2 minus 1, which is also an integer, okay? And you can take powers and so on. So what does it look like? It looks like when you take such elements and you view them as acting on the square, okay? Because after all, the space of adels, what replaces the adels, if you want, is just R cross R, yeah? Okay, so you're acting by R cross R, on R cross R, but how are you acting? You're acting by pairs, of the number, and like it's inverse because the product of the norms have to be equal to 1. Okay, so you have really an hyperbolic action whose orbits are lying on hyperbolas, like this, okay? When you look at the elements which have non-zero coordinates, okay? So, you get orbits of this type, okay? When you take an element whose two coordinates are non-zero. If you take an element which has one coordinate, like the x coordinate, which is 0, what do you get? Well, you get R star divided by the units, okay? But that's a very nice thing. In fact, this R star divided by this is just a nice little circle, okay? And this circle, what is it? It is exactly the orbit of the Frobenius over the corresponding place. Okay, that's really what it is. Now, if you look at the other place where one coordinate vanishes, the other, so the y coordinate vanishes, and this coordinate doesn't vanish, you also get another circle. Okay? So what is the overall picture? The overall picture is that, first of all, you have a cylinder. Okay, you have a big cylinder, because when you divide the non-zero coordinates by the units, you get a cylinder. Okay? This cylinder is mapped properly to R plus star by the module. Okay? But it's compact otherwise. And then on top of this cylinder, you have these two circles, okay, which correspond to the orbits of these things. And then you have 0. Okay? 0 is also a point, but as I said before, it's an orbifold point. Namely, it is really 0 divided by z, okay, which is a group of units. Yeah. Okay? And now all of these are fitted together in some topology, which is tricky, okay, which is a quotient topology. Now, which is such that this thing is dense, so it touches these two circles. Okay, it's like a generic point. So you have these two circles, and these two circles also touch at 0. Okay? And 0 really does not exist because it's divided by z. Okay? Now, you can take this example. Let's take another example. This example, the space, this adelic class space, still looks sort of feasible somehow. So let me show you another example to show you that it is as tricky, really, as the global space. So, second example is the following. Let's take k equals rationals, q. Okay, and let's take now 3 places. So let's take S to be the set which is the infinite place, and the numbers 2 and 3. Okay? So in that case, what is the, first of all, what is the S units? So the S units, they are things which, because we put in the infinite place, okay, what they will have to be, they will have to be elements of the multiplicative group which are powers of 2 and powers of 3. And there is still a plus or minus sign in front. So OS star in that case, the group of S units, is equal to plus or minus powers of 2 and powers of 3, okay, where n and m are integers, n and n are in Z. Okay, and where do they act? They act on a product space, which is the 2 adelic numbers cross the 3 adelic numbers cross R. All right, and how do they act? They act by powers of 2 and powers of 3, okay, in each piece, of course. Now, this action very much resembles this action here, okay? It resembles very much. In other words, you see, you have now a 3 space, not a 2 space, okay? And whenever you consider one of these axes and so on, when you consider, one coordinate vanishing, and you divide by this, you will again get a very nice sort of orbit of Frobenius, exactly as before. But observe one thing, which is that if you consider now 1 cross 1 cross R, sorry, 0 cross 0 cross R, okay, then you see that the action of 2 to the n and 3 to the m on R is ergodic on R, okay? So here you meet a very wide space, okay? And of course, I mean, so it is a very tricky space indeed, okay, this adelic space. You can see it already. So you can see it already that as soon as you have more than 2 places, strictly more, like three places and so on, these places look very much like this. That over each place, there is a corresponding orbit of Frobenius, which has the right length, which is exactly, you know, like in the case of finite fields, where over each place you have the finite number of elements which correspond to the orbit of Frobenius. You have a generic orbit, which is the dense thing, okay? But then you have some really tricky non-commutative glue, which is holding things together, okay? And which is coming from such stuff, okay? Now, if you look a little more closely, you can compute what is, for instance, in that case, of Q square root of 2, you can compute, for instance, the contribution of 0. Okay? Let's look at the contribution of 0. Now, the contribution of 0, if you look at the contribution of 0, what will you get? Because it's an orbifold point, you will get 1 over the order of the point, which is infinite. Okay? Multiplied by a sum. Okay? I just apply the general recipe. I mean, it's R squared, and I have an action, and so on. Okay? Now, you get a sum, but in that sum, now it's a sum over the group OS star. Okay? And okay, so you take an element of the ideal class group, the corresponding ideal class group, and what do you have? Now you don't have just 1 minus lambda, but you have an expression which is like this, that you have 1 minus q lambda, and you have 1 minus, I would have to be careful, but you see this is like minus q, there are 2 places, so let me call them v1 and v2. Lambda v1, and 1 minus q v2, lambda v2, something like that. Okay? Now, what do you know? You know that q v1, q v2, in absolute value, this product is equal to 1, because you are dealing with units. Okay? And you make a sum. So these only depend upon the parameter in z, because the group of S units is really the same thing as z. Okay? Now, if you compute this sum, you will find out that this whole sum is actually finite, because it's a geometric series. On z, it's a geometric series for when the z goes in the plus direction, and it's a geometric series because of the other term when the z goes in the other direction. Okay, this is what you find out by computing. So in fact, this is very reassuring, because you know that there is a contribution, okay? But this is finite, and it's divided by infinity, because this is the order of the orbifold point, okay? So I mean, this was sort of the early reason why, in fact, the sort of rough motivation which I had given, if I should go through now. So now you can go much further at this level, but of course this is not a proof. I will give a proof. Now, at a much further, I mean, what you can say.
Confused maybe the OS star. OS star is z plus z plus z.
No, I am in the example 1 now. I am in q square root of 2. Okay, if you do it for this one, it will be very similar, but you will have 3 terms.
Yes.
Okay?
Yeah.
Okay, and in these 3 terms, you will find that they depend on z plus z, but it's again a geometric series. Okay? You see, I mean, what could have happened, which would be wrong, would have been if you divide by infinity, but you have something which is infinite, because that's, you know, that has a tendency to give you a result which is non-trivial. Okay? Nevertheless, it's finite, this sum. Okay? So now, for a very similar reason, it turns out that when you compute the contributions of something like these actions by power of 2 and power of 3 on the real line, for instance, you again find 0. And the reason is that the covolume in the closure is actually 0. But that's, you know, that's something which now has to be put on a very firm footing. And I mean, this was only very unsatisfactory answer. Okay. So now what I want to do, I want to completely analyze this local situation. I mean, with finitely many places. But you see that by doing it, we are not wasting time, because we are already, in the sense of non-commutative geometry, in very subtle situations which are not of type 1. Because precisely you have these ergodic pieces and so on. So I mean, it's not at all a trivial space that you get by finitely many places, by no means. Okay, so let's do it. So we shall need a lot of lemmas, technical lemmas, because as I said, the reason why the thing is actually, the formula is actually correct, I mean, the reasons are not obvious at all. They are because 0 doesn't contribute, because multiple places don't contribute, and so on and so forth. Okay, so it cannot be too simple. All right, so how will it go? So what I will have to do, I will continue on the other blackboard. So what I will have to do really is to first of all do the same analysis of what is L2 as I was doing in the case of the others. What is L2? And then once I will have analyzed what I will have as an L2 space and so on, I will not use the delta, the parameter delta, because I will proceed exactly as in the case of local fields, where there was no parameter delta. Okay? And then we shall prove the analogous theorem to what we had for local fields. Okay, so the first aim will be really to define correctly the L2 space for the space of adelic classes. But I remind you that these adelic classes are only for finitely many places. Okay, so I will proceed in a way which is entirely parallel to the case of all adels, which means that I will take the Brouwer-Schwarz space and I will define a Hilbert space norm on the Brouwer-Schwarz space. Let me write it over there. Okay? So what do we want? We want to take this space which I will call A sub S, which is the product of the local field for V in S. Okay? And the corresponding quotient space, XS equals AS mod OS star. Okay, the first thing that we want is we want to define L2 of XS. Okay, because I said I don't put the delta. Because we shall see much later that the delta is not necessary. It will drop out. Okay? So what should be L2 of XS? I could put the delta if we wanted, but I mean it's not necessary. Okay? So, so now I want to define for a function xi, so xi of x is a function, so xi belongs to the Schwarz space, the Brouwer-Schwarz space of S, and I want to define the L2 norm of xi squared. So I don't repeat what I said many times, I just write down the formula. Okay? We are relating the upper space with the downstairs space. How do we relate them? Just it will be an integral, okay? And it will be the integral of what? Of sigma of the function of qx, as usual. But of course now q is in the s units, absolute value square. Okay, so you integrate this function exactly as we were doing. And now I want to put dx, the R measure. But I know, because I have finitely many places on me, that dx is exactly up to scale the absolute value of x times g star x. Okay? Now, how do I normalize g star x, the modificative R measure? The modificative R measure I will normalize in such a way that if I take D, a fundamental domain, okay, for the action of OS star. So remember OS star was acting here. For OS star acting on the GS, which is the product of the K star D, okay, what I would like is that the restriction of D star x, so D star x is a measure here on JS. Okay? So what I want is that the restriction of D star x to D is the R measure D star x on CS, which is deltas. Okay? And that one is normalized as usual, namely that if I look at the elements which are normed between 1 and lambda, they will go like log lambda. Okay? This is usual stuff. Okay? Now, what do you see? You see that, up to a set of measure 0, I mean, JS is the entire product of KD up to a set of measure 0. Okay? So when I take this integral, I have a fundamental domain when I want to integrate. So I can integrate just over Z. Okay? I mean, it is the same thing, of course, as to integrate over the quotient. Okay? But you see that this formula is entirely analogous to what we were doing for the overall thing. Okay? All the adelic aspects, the overall thing. Whether I put T here or whether I put the integral of the quotient is the same, because the function which is invariant under the action. Okay, now what is is that this makes sense. So the first lemma will comprise 3 items. So this is the first technical lemma, where we shall begin to see something. So lemma 1, if you want, will comprise 3 things. The first thing would be that for any, sorry? That's my point. Let me explain this. Okay. So the first point is that for any psi transverse, okay, the norm of psi is finite. Okay? That's not obvious, as we are pointing out. Okay. Okay. So the norm of psi is finite for any psi transverse of AS. Okay. The second point is that in fact it's given by a very nice geometrically convergent series, namely that norm of psi squared is equal to the sum over OS star of what? Of the inner product of psi with what I will call U of Q times psi. So Q belongs to OS star. And this is an inner product now on the adelic space. So not downstairs. You see there is an upstairs and a downstairs. Okay, I suppose this is very clear. So this is an inner product upstairs. And U of Q is defined by U of Q of psi of x, as usual, is psi of Q and S. Okay? As usual. Now the third, which is the most interesting, because I don't think it is so trivial, is the following, is that the norm of the Fourier transform of psi is equal to the norm of psi, okay, where f is Fourier relative to the basic character. Fourier relative the basic character alpha of what? Of alpha, if you want, it's a Poisson product. I mean, it's Poisson product of alpha sub okay, I mean, there is a coefficient here, but if you normalize correctly, the alpha okay, in L2 scale. Right? Okay, so let me prove these various things, because indeed, even the little a is surprising. Okay? I mean, certainly none of this, that little a is true. So what is really going on? What is really going on? Okay? Look at the corresponding space that we have. Now, that space, let's look at it for Q of square root of Q. Okay, just to get something. Now, what are the functions in the Breuer-Schwarz space which bother us? There are functions which don't vanish at 0. If they would vanish at 0 or near 0, okay, I mean, the situation is a problem. So in fact, we take the function which is just a characteristic function. So let's take psi of x, okay, equals 1 if x is less or equal to 1 for any t less, and 0 otherwise. Okay, so I mean, this is a characteristic function of the cube, of the unit cube. Okay. Now, what we have to convince ourselves of is that when we take this integral, the integral is actually finite. Okay. So, in order to prove that, what we shall prove is a sub-lemma, which is the following, which is that if we call E0 of psi of x, the partial sum, namely the sum over Q in OS star, of psi of Qx, okay? Now, because remember that the group of S units is co-compact in the group of ideals of absolute value 1. Okay? So it is clear that this only depends up to a compact piece of the norm of x. Okay? I mean, it's really a function which really depends on one parameter, which is the size of the norm of x, and which could get wide when the norm of x goes to 0. I mean, if the norm of x is non-zero, it means that none of the components of x are 0. It means that you are in the generic orbit, and this is convergent, because the action is proper. So the existence of the sum is fine. What we want to understand is its behavior when the generic point converges to the non-generic orbit. Okay? Now, so what is it? Now, the claim is that this, in absolute value, is a big O of a power of log of norm of x, some power, okay? Okay, when the norm of x goes to 0. Okay, so we shall prove that. Okay. Now, if it is of the order of log to some power, we know very well that the log, is integrable near the origin for the additive armature. So we are in business. Okay? If you want, when you look at it multiplicatively, this is saying that because here you have x and this star x, and this is like exponential minus s, and the log is like s to some power. Of course, it's integrable. Okay? Fine. So let's do that. What is the reason? Well, the reason should be pretty obvious. See, the reason is the following: is that when we look at this hyperbolic action, okay, it's really an hyperbolic action. So, because the group of S units is co-compact in the group of ideals of modulus 1, okay, we can really replace it by the action of the ideals of modulus 1 to evaluate this integral. This is sum. And we can replace the sum by an integral. Okay, because you have disjoint balls. Okay, we are seeing that fine. So in fact, what we are really doing, we are really evaluating an integral here, which is the intersection of this hyperbola, okay, shifted by x when you go to 0. Now let's compute it. Okay? So what is it? I mean, the best way to parameterize this thing is by e to the u1, etc., e to the um, where m is the number of places which are involved. Okay? And where sigma of uj is equal to 0. This condition that sigma of uj is equal to 0 is exactly the condition that the product, okay, is equal to 0. Of course, here I am dealing with real places, but I mean, it's exactly the same when you deal with PID just by looking at the volume. Okay? So look at this now. Now, what are we evaluating? You see, this is now the point we are looking at is like of the form lambda e to the u1, etc., lambda e to the un. Okay, up to a compact discrepancy. Because as I said, okay, we look at the points, there is only one scalar which is involved, up to a compact. So we are really looking at these points, and now we are asking which among these points for lambda small, close to 0, are belonging to the square, to the cube, the unit cube. Okay. So the condition is simply that lambda e to the ui in absolute value is less than 1. Less or equal to 1. Now what is this condition? This condition is telling you that ui plus log lambda, remember lambda is small, is less or equal to 0. Okay? And what are we integrating? We are integrating, in fact, the volume in the DUIs, okay, with the condition sigma of uj equals 0. Because that's exactly the multiplicative armature on the corresponding group. Okay, I suppose this is here. Okay. But what are we doing really? We are taking an hyperplane, like in the proof of the Dirichlet theorem, we are taking an hyperplane in some m-dimensional vector space. Okay? And we are looking at this condition. But you see, if you look at this condition, this thing here, you will have UIs which are positive and UIs which are negative. Those which are positive, I will put a plus. Those which are negative, I will put a minus up there. But it is clear that because of this condition, it's also the same thing as saying that sigma of uj plus is equal to sigma of uj minus. Okay? I mean, that condition is the same. Now, the fact that this is less than 0 is telling you that the supremum of the UIs is less than minus log lambda, which if you want is log of 1 over lambda. So in fact, what do you know? You know that all the uj plus are less or equal than minus log lambda, which is log of 1 over lambda. And the uj minus, okay, because of this equality, they are less than some constant times log of 1 over lambda. Okay? Just because of the condition. I mean, there are m of them. And of course, if I, okay? And this constant is, if you want, m. So, what does this mean? Well, this means that, in fact, we have, because uj plus and uj minus are positive, we have a bounded cube in our M, okay? And we are looking at its volume. So this volume is majorized by the size of the cube, and the size is a log power. Okay, so we are in this. Okay? Lambda is not normovex. Okay? I will give another proof. I mean, in B, I will give another proof. So that's why I'm not so patient about this proof. But I think you should convince yourself really, that if you intersect such a cube with these hyperbolas, Okay, I mean they grow like a logarithm, like a power of log. Okay, so because they grow like a power of log, we do not have this problem that we had in the case of the total adelic space. You see, this is much more sparse. The group of S units is much more sparse than in the global case. Because in the global case, you have all the non-zero elements in the lattice. That is much denser, and that approximates the Riemann sums. And this is why you have divergence. But here you don't have divergence. Okay. Here it's only logarithm. So that's for the first one, first stage. So this means that the Hilbert space is completely canonical, because there is none of these linear conditions that I have to impose. I have to impose two linear conditions. Okay? So I don't have to impose that. Now, let's look at this. Let's look at this thing. So in fact, one should add the lemma, and I did that this in the statement. In fact, this series here will be geometrically convergent. Okay, so what do I mean by this? You see, the group of S units is an abelian group, so OS star is an abelian group. And what does the Dirichlet unit theorem tells us? You see, this abelian group is in fact commensurate to a lattice in R to the power of the number of places minus 1. Okay, this is the unit theorem of Dirichlet. And it's achieved, if you want, by the following map. So there is a very canonical map, which I will denote by L, which goes from this group, which is an abelian group, to R, to an hyperplane, H, which is contained in R to the S, where S is a set of places. And this map L is defined simply by the condition that L of an element Q is the collection of the logarithms of the norm. Okay? Okay, in other words, I look for each place at the log of the corresponding norm. Okay? Because the product of the norms is equal to 1, of course, I know that the sum of the logarithms is equal to 0, so I am indeed in this hyperplane. And the statement of the Dirichlet unit theorem tells you that what you have is a lattice, okay, which is co-compact. I mean, you have a lattice in this hyperplane. That's very simple. Sorry? Yeah. That's why you need to have all the infinite places. I mean, if you didn't have all the infinite places, that wouldn't. So you have this map. So this means that we understand this abelian group pretty well. And in fact, we can say the following. We can say that we have an inequality of the following form. Let me see. That the supremum of these norms, Q sub p, I claim, will be bigger or equal to the exponential of the distance between Q and 1, where D is a suitable word metric on OS star. Okay. So by word metric, for a finitely generated discrete group, you count how many generators you need to write a word. Okay. I mean, overweight. But here, because we are dealing with a group which is commensurate to a lattice, this is any metric which is induced by the corresponding Euclidean metric in the hyperplane. Okay? That's what we are doing. But we can scale. We can scale up. Okay, and why is this true? Well, essentially, I already made the reasoning, you see, because if you call log of Q sub p, let's call it U sub p. Okay? All right? Now, these numbers are real numbers, and they add up to 0. Okay? You know that. Now, the supremum of QV is related simply to the supremum of the U sub p by an exponential function. Okay? But the supremum of the U sub v, now, I want to tie it up, okay, by an inequality, to the Euclidean norm of U. Okay? I mean, in the hyperplane H. Now, that Euclidean norm, what will it involve? See, it will involve, for instance, something like sigma of uv plus sigma of uv minus. Okay? That's a Euclidean norm. But that Euclidean norm, we have seen, is smaller or equal to than m, okay, where m is the number of places, times the supremum of the UV plus, because the UV minus were related. So it's fine. Okay, so we do have an inequality. You want that the Euclidean norm is controlled by the supremum of the positive pieces. If you exponentiate that, what do you get? You just get this, okay? Because the supremum of QV is the supremum of the exponential u sub v, and this is the exponentiation of the work, which is the distance from QV. Okay? Okay, so this is quite simple, and it just tells us that the way we control the size of elements, when I talk about the geometric series, so if I want to explain that this is the geometric series, I have to convince you that if I take the inner product of psi with u of q of psi, this decays like a geometric series. See? And then I have to prove that it is equal to the norm of psi squared. So why is it a geometric series? But for that, there is nothing better than a picture. Okay, so I will use this for picture. The point is the following. The point is that what does it mean to be in short space as far as size is concerned? Because after all, we only have to control the size of the function, the rest of the values. What it means really is that the function psi here, I can write it as psi of x in absolute value is less or equal than the sum of a sequence of rapid decay, lambda n, times a function kn of x, and we denote by kn of x, where kn is a characteristic function of the set of x, so that x sub v is less or equal to n for any place between s. Okay? In other words, what I am telling you is something very, very simple, is that the Schwarz function is less than the sum of characteristic functions of cubes, where the coefficients which I take are of rapid decay. Okay, this is true for any field. So I don't have to worry. I want to do something very general. So you see that you are reduced to an estimate, and you are reduced to estimating the size of kn inner product with, let us say, u of q inverse times kn. I put q inverse, but I could put q just for convenience. Now, why do I put the same n here? Because if I put different n and m, it will always be majorized by the largest of m and m. So I mean, there is no point to keep them separate. Okay? So you see, I am trying to estimate this size. What is this size? Kn is a cube, like this cube. What is u of q inverse kn? It is a transformed of the cube by these affine transformations, okay, which is k and so on. So it looks like this. Okay? I mean, it's not a cube, it's a rectangle. You see? U of q inverse kn is a rectangle. So, I mean, so it's a characteristic function. So u of q inverse kn of x, it's equal to 0 in many cases, but it's equal to 1 when, what happens? So you see, this is equal to kn of qx. And that means that I have to have that qx, qv, xv in norm has to be smaller than n, okay, for any n. And that means that xv has to be smaller than n qv inverse. Okay, so this means so that xv is smaller than n times qv inverse. Okay? Now imagine that qv inverse is quite large. Then this rectangle is quite thin. You see, it looks much more like this. Okay? But if you take the product of the two rectangles, the two characteristic functions, it's only their intersection. Okay? And because the rectangle got very thin, the intersection will have a measure which is much smaller. So it's obvious that the inner product will be majorized by, because I have QV inverse, by some power of n to the power of the number of places, okay, times the supremum of the QVs, but inverse. Okay? Now, by what we have just seen previously, this is a geometric series because this is less or equal to n to the m, okay, times the exponential of minus the word metric distance between Q and Y. Okay? Now I have coefficients which are of rapid decay. Remember that I have this coefficient of rapid decay. So when I do the inner product of psi with U of Q inverse psi, okay, what I will get is that in absolute value, just a gross estimate, this is smaller than the sum of lambda n1, lambda n2. Then I have n1, n2 to the n. You see, I mean, I can obviously replace the supremum of n1 and n2 by the product. So n1 and n2 to the n. And then I have the exponential of minus d of q1, which appears here. Now this sum is finite, uniform. Okay, and this is a geometric set. So what we have seen, that's a very important point, is that this series is geometrically convergent. Okay, I mean, that's absolutely a key estimate. Now, why is it equal to norm of psi squared? That's Fubini. Let me explain. I will start again from there. But that's just Fubini. You see, because when you expand that norm here, when you expand that norm, you, as I said, this is dx. Okay, this is dx. And when you expand that norm, you can raise to the square, and then you will have a double sum. Maybe you will have a sum with you have q1 and q2. If you have integral over d now, you will have a sum of psi, double sum with psi of q1x, and you will have psi of q2x. Okay, perhaps a bar, but I don't care. And then I have dx. Okay, and it's the integral over d. But you see that you can match together a q1 with a d to do the integral over all x. Okay? And then you are in business. Because it remains to use the q2, q1 inverse. Okay? And that's geometry. And you see, it's quite obvious that the Fourier transform is actually an isometry. If you try directly to prove that Fourier transform is an isometry, you get nowhere. Because you see, but we shall see that that is an isometry for very simple reasons. The space of adelic classes is replaced by the quotient of this product by the S units, which are a nice discrete or compact subgroup of the details of modulus 1. There is a direct definition of L2 of the adelic space. Okay? By using this norm, and we were proving the lemma that this norm is automatically finite for any function in the lower short space. So there is no condition like psi of 0 equals 0 or whatever. Okay, we prove that by showing that this partial sum has a behavior of a low power for absolute of x going to 0. There is this sort of generic orbit. So what we saw is that the picture was that there was, when you take several places, but there was one generic orbit, okay, which was coming from the points xb, so that xb is different from 0 for any. And then on the hyperplanes there were like the orbits of the problems, which were lying on each of them. Okay? And then there were non-commutativity entering the place, the near odicity of the course of these harmonies. Okay. Now, so there was some simple things of normalization, and the first lemma of analysis was really the following: that first of all, any function in short space has a finite norm. Okay. Second of all, the square of the norm can be written as a sum of a geometrically convergent series. It's convergent on this abelian finitely generated group of the inner products which were taken over the adels. Okay. And we showed that. Okay. I mean, there is a Fubini, as I said, I explained two words. There is a Fubini argument to conclude, but it is there. Now, the very interesting consequence, and I think very non-trivial consequence of this equality, is that the Fourier transform, the ordinary Fourier transform, on top, at the level of these adels here, is actually an isometry of this space. Well, of course, there is a normalization. Now, the reason why it's an isometry is not Poisson, because the S units do not form a lattice. They do not form the non-zero points of the lattice by any means. But this is a replacement for Poisson somehow. And how is it proved? It's proven because the norm square is given by this series. So we just have to analyze what happens in this series. Now, if we replace psi by f of psi, by the Fourier transform, the term will be f of psi times u of q times f of psi. Okay, f is a Fourier transform. But what do we know? We know that u of q, which is a shift operator, I mean the scaling operator, does not commute with f, but satisfies u of q times f is equal to f times u of q inverse. Okay? And this is just the obvious transformation of Fourier. So this means that this term is equal to, now I put Fourier on the other side, but I pick a q inverse, but Fourier is an isometry up to scale, so it is equal to psi times u of q inverse psi. Okay? And of course the summation over q is fine, and gives a right result.
Part B, just disintegrating
No, part B is just disintegrating
volumes
on
domain.
over the domains, but remember that see, this is a square, so you have two q's.
But the point is that this is on the adelic.
Sure, this is absolute.
The smaller one.
Right. Let me explain this point, because this point is important. You know, psi square, okay, is given as an integral over the fundamental domain of the square. So let me spell out the square. So the square is sigma of q1x, okay, times sigma of psi of q2x. Okay, now there is a bar. Okay, and dx. Okay. Now, when you write this, there are two q's. Okay? So I can use one q to combine with the fundamental domain by the dressing. And I will remain with the ratio of the two q's. And this ratio is exactly right. Okay, exactly. So this is why, you know, when you apply Fourier, if you would apply Fourier directly, you wouldn't see anything. Okay, so what we have now, we have a nice Fourier transform. Okay, so now we can formulate the cutoff. All right. Maybe now we have the inverse space. So the inverse space is L2 of xs. Okay. And we have the action u of g, where g is an element in the ideal class CS, because CS is a quotient element u of the corresponding inverse in the product of k star g by the local units, S units. Okay, by the S units. So the group CS is acting, and how is it acting? It's acting by u of j psi evaluated at x is psi of g inverse x. Okay, and for the same reason as when we are dealing with the total thing about this, this action only depends on the ideal class, but not on the ideal itself. Okay. So in fact, now we can consider the operator t, which is integral of h of u inverse. So h is again a function of the ideal classes times u of u, sorry, h of u. Times d star u, okay, and the integral is on CS, and I remind you that CS has a fundamental domain, okay, which is domain D. Okay. All right. So now what we want to understand.
So how do you see its log or something?
Oh, that's I explained. It's not obvious. I mean, it doesn't take much, but let me explain which is equivalent. Why this series is geometric equivalent. Takes a basic function, characteristic function of the cube. Take how it transforms. Transform it into very slim rectangle. Okay. Derivation of the cube. So you get only this. That's.
I got it.
Okay. All right. So so now what we have to understand is how to compute the trace of t, as always. Okay. And for this we do the cutoff. So the cutoff will be done as follows, exactly as before. It will be done by, it took me a lot of time to find this cutoff, because I was trying to make cutoffs by cutting off at each place, which was a big mistake, because this is not gauge-invariant. You see, in that situation, it's exactly like gauge theory in physics. There is a gauge group, which is this group OS star. It really plays a role to gauge group. Okay? And you know in physics that it is a big sin to make a cutoff which is not gauge-invariant, because then you can produce all sorts of weird stuff and so on. So you always have to fix a cutoff in a gauge-invariant manner. Now, how can you do that here? Well, you can do that by the following. You can define the projector lambda, okay, on L2 of xs. Okay, and this projector P lambda better be invariant under OS star. Okay, but we know that it has to take into account the infrared divergence. Maybe it should cut off the space xs. But, so at first what I was stupidly tempting to do was to cut it off by a big box like this. Okay, that's wrong. What you have to do is to take P lambda to be a multiplication operator, so that P lambda of psi at x is just rho lambda of x times psi of x. And rho lambda of x, what is it? It is a function which is equal to 1 if the norm of x is less than or equal to lambda and 0 otherwise. Okay? So it is our familiar saying. But now if you look at it, it looks weird. Okay? It looks strange. Because that function, you see, it is a characteristic function of a big hyperboloid. Okay? Which is so sitting here. Okay? Because it's telling you that the product of the norms, that norm here, is equal to the product of the x subclass. Okay? So in fact, what you are talking about is not a compact piece. You are talking about a piece which has a lot of cusps. Okay, so this is our cutoff function for this, but now because we have the Fourier transform, and we know that the Fourier transform is an isometry, we can talk about the Fourier transform of P lambda. So in fact, we have P lambda at, which is Fourier times P lambda. And I mean, this doesn't depend on one side or the other. Okay, we have R lambda, our saying, which is P lambda at times P lambda, and I mean that should take care of both the infrared and ultraviolet risks. Okay. So now let me state the theorem, and we insert delicate proof. So the theorem is the following. Okay. So setup is the same. So we have h, which is a function in short space, which is compatible on the class CS. And we look at the operator T, which is u of h. Then we multiply h u of t. The armature here is normalized as always on the delta. And now the statement following is that the trace of r lambda times u of h is equal to 2 log lambda, log prime lambda, because there could be, we could be in the finite field case. I mean, there could be only a non-Archimedean case. It's 2 log prime lambda times h of 1 plus. Now it's not a single term, it's a sum over all the places which belong to S. Okay. Of the integral prime that depends on the Fourier transform. Okay, as before. Of h of u inverse restricted to the local field k star b embedded in the delta group, CS, by the inclusion where lambda goes to 1, 1, 1, 1 everywhere, except lambda somewhere. Okay, lambda is basically. Over 1 minus u and this star b. And this is the normalized armature of k star b. So it is on the nose the Dirichlet formula. Plus little law of 1. In fact, it's little law of lambda to minus 1. Little law of 1. Okay. So this is a statement. Now, as I said, if you had such a statement for infinity many place, you are done. You prove the Riemann hypothesis for all L functions. Okay, so let me explain how this is. Because indeed the proof is quite delicate, but much more delicate than what we were doing the last time. Okay, so maybe I will just erase here and continue to all right. Okay, so let me remind you of what you do in the case of the Zellberg-Trace formula, and we shall do the same. Okay, because first of all, we have, exactly as in the Zellberg-Trace formula, we have a situation where there is a downstairs and an upstairs. Okay? I mean, there is an upstairs, which is what happens on the other. Okay, I mean, the product of the local fields. There is a downstairs, which is what happens on the other class space. So, I mean, at first, what one does is one does exactly as in the proof of the Poisson summation formula. Namely, one relates the upstairs to the downstairs. Okay? And you do that like this.
Yes, how does the rho lambda multiply grow to what?
Why is P lambda preserved short space or something? So
You see? No. This was the whole point to prove that Fourier was an isometry in L2 because I don't care.
It doesn't care about
I don't care about
it. Doesn't care about does it preserve it though? No, that's the problem.
I mean,
That's why
it preserves it for non-Archimedean places.
Yeah.
Otherwise, you'd like to split it a little bit.
Yes.
But it preserves. But we don't care because it's an isometry. Because forget it. Okay, so in fact, I mean, in many instances, we shall be dealing with operators which exist both upstairs and downstairs. Okay, maybe we shall be dealing with operators which exist upstairs, but not necessarily preserve short space. I don't care that they preserve short space. Okay, in fact, they should map like short space to the dual short space. That's good enough. Okay, what I want is that they have a short kernel. So I consider operator T, if you want, which are given by T of psi. Let me first, this is upstairs. So this is upstairs. Okay, and upstairs they can be written as T psi of x is equal to integral of a short kernel, K of x y, psi of y dy. Okay? But they are such that they commute with the action of the local units, yes units. Namely, that they are such that they satisfy K of qx, qy is equal to K of xy. Okay? There will be plenty of such operators. I mean, the first example, of course, is the operator that we had, which was integral of h of lambda u of lambda d star lambda. And this we can write as you see, I don't want to write it downstairs also for the Edel class group. I want to write that the Edel class group, CS, is a quotient. So that I want to write by projecting down again, exactly as in the proof of the Dirichlet formula, or the Poisson formula, from a function h tilde, okay, which is also smooth and nice, but which is a function on the Edel group. Okay? Namely, this will be equal to the integral now over the Edel, JS, which is a product of the K star D, okay, or some function which I will call h tilde, okay, whose corresponding automorphic function is h, okay, h tilde of lambda, but okay, h tilde of lambda times u of lambda. But now let me give the corresponding kernel, because the kernel of u lambda, we know, so let me put a lambda inverse, and let me put a lambda inverse, which is perfectly valid. Okay, and u of lambda inverse, we know that the corresponding delta distribution, if you want, is delta of y minus lambda x, okay, dy, so dx. Okay. So in other words, from this, we know what is k of xy for the operator that we have here, and the k of xy is equal to the integral of the lifting function, which is not unique. I mean, it's only properties that when you average it, you get h tilde of lambda inverse, times delta of y minus lambda x. Okay, times this term. So this will be useful. Okay, that's one example of a kernel which certainly satisfies k of qx, qy equal to k of xy. But now we have to find, so there will be a similar kernel for r lambda, for the operator r lambda, which is a product, if you want, of rho lambda, so p lambda, by the Fourier transform of p lambda by p lambda. We shall write the kernel very shortly. Now, I want to make a few generalities about these operators. Namely, when I have such an operator, which is given by an invariant kernel upstairs, I can push it down. Okay? I mean, it defines an operator downstairs. And the corresponding kernel, so the kernel downstairs, okay, it's just given by the sum of k of qx and y, okay, where q belongs to OS star. Okay, that's clear. Now there is one thing which I want to use, which is the following, which is that this map from upstairs to downstairs, this is sort of pi of k, some sort of projection of k. I want to check that pi is a homomorphism. I mean, pi of k1 times k2 is equal to pi of k1 times pi of k2. Okay? I mean, this is sort of clear because if you take pi of k1, k2, yeah, well, it's not so obvious because you are not in the same inverse space. Okay, if you want, a function is clear. So we have pi of k1, k2 is equal to pi of k1, pi of k2. That's okay. And Also, I want a formula for the trace, exactly as in Weber. Okay, namely the trace of pi of k. Okay, it is the integral of the diagonal value of pi of k. But of course, for that, I have to bring in the summation over q here. So this will be an integral over x in the fundamental domain D. Okay, because this is downstairs. And it will be a sum also. I can put the sum of the integral as I want. And it will be k of qx and y. And I can put the q, sorry, the x and dx. And I can put the q where I want. I can also put the q here if I want and so on. Okay? Also now what I want to do, I want to combine this and that and compute the trace of the product of two operators. And I want to make a little jargon into it. Okay? So imagine that now I want to compute the trace of pi of k1 transpose times pi of k2. And this pi of k2, I will call it k because it will be our k. Okay? This will be the kernel R lambda transpose. Okay? So if you do that, because I put a transpose here, there will be an integral on the same variable. Okay? Because I do the pi of k on both, I will have to make a summation in q on both. Now what I claim is that there are two summations in q. Okay? What I claim is that I can get rid of one of these summations in q and replace it by an integral dy. So I claim that this is equal to the integral of k1 transpose, sorry, k1 of, it should be like qx and y.
It's the same thing before.
Exactly. It's exactly the same thing. And the second should be k of xy. So stop me if I am wrong, but it should be an integral in x in d and all of dy. Okay? Okay? I mean, this follows from the fact that pi is homomorphism, so I can use the summation over y upstairs. Okay, you can check it in the ways. So let's apply this now. And let's write what we are after. So what we are after is u. Sorry?
Why was there a multiplicative measure?
It's a summation over q. Yes? One is?
Why is that?
Both are. Yeah. No, but this is the additive. But it's on the fundamental domain. So it's fine.
It's on the smallest set.
Okay, it's on the smaller set. Okay, fine. So let's look at this. So what we have now, I will replace the corresponding kernel by their value. So what we are after, if you want, is a summation over q of some integral iq, okay, which I will have to compute. And the integral iq now is equal to the integral over the fundamental domain, so x in p, okay, of the transpose of R lambda transpose at qx and y. And then this guy, k of xy, dx dy. Okay, so that's really what we want to understand. Fine. All right. So first of all, we need the kernel for R lambda transpose. Okay. Now this is a kernel upstairs. Remember. Okay. And remember that Fourier was going down, but it was really the ordinary Fourier upstairs. So to compute this kernel upstairs, again by the fact that the homomorphism is a homomorphism for kernels, we can just do it there. And we find that R lambda transpose of x and y is equal to rho lambda of x, okay, dispersed, times rho lambda of x minus 1, rho lambda full. Is that clear? Okay.
Why is it clear?
Because this is the Fourier transform, the kernel for the Fourier transform operator. I put the Fourier. Okay, this is a convolution operator, which I use as Fourier. But this is upstairs. Okay, all of this is upstairs. All these operators are commuting with the action of the S units. Okay? Very good. Fine. Okay, so now what do we have to compute? We have to compute the following expression. You see, and we shall have to solve there over Q. So IQ is equal to the integral over the fundamental domain, for the multiplicative action, or OS star, of R lambda transpose, but this is rho lambda of x, times rho lambda at Fourier of x minus y, times k of xy, which I will replace by its value. So it's h tilde of lambda inverse times delta of y minus lambda x d lambda dx dy. Okay? Fine. All right, so let's, this is where the theory of Fourier integral if you think conceptually. See what, in order to compute this integral, of course we shall use the same trick as we used before. Yes.
Where's Q in this? Okay.
Where's Q?
No, it's that.
Yeah, you're right.
QX.
Anything Q
It has to evaluate the QX.
Qx.
Oh, okay.
Some of it.
And he
Well,
has
let
to
me put the Q on the other
Q.
side. I am allowed to do that. It will be fine.
Put it on the, put it on the LB.
I know.
I
Okay.
see.
Okay? It will be fine. Okay. So I put it here. Now, I do the computation exactly as before, namely I do a partial Fourier transform by putting y equals x plus a and Fourier in it. Okay? And I use Parseval identity. Okay. So rho lambda of x is not touched. Here I have y equals x plus a. So this is just rho lambda at of a. And I do Fourier. Okay, and I cut here when I do Parseval. Okay. So if I do Fourier here, I will get rho lambda of psi. So I mean it will be integral. There will be rho lambda of x. There will be rho lambda of psi. Okay. This will be cut. And here now, I will have, because I do y equals x plus a, I will have y equals x plus a. All right. And I will have to integrate, we will take Fourier with respect to a. So we have to take Fourier with respect to a. What does it give us? It gives us integral of h tilde, h tilde of lambda inverse. This is a tilde, it's not Fourier. H tilde of lambda inverse. Then I have delta of x plus a minus lambda qx. Okay, then I have dA, d lambda, and so on. Okay? And the integral is really dA, which I haven't mentioned. Now if I integrate, sorry, I forgot, alpha of x side, because I am taking 4. Okay? Or it takes a car. Now if I do that, this term here tells me that a has to be equal to lambda q minus 1 times x. Okay, so in fact, I have to take this and replace a by lambda q minus 1 times x. And so I want absolutely to save this formula, so I will save it here. So what do we have? We have that the second term, so that means IQ, the integral of term, is equal to the integral. So now it's x less than lambda. It is psi less than lambda because of the rho lambda. Okay? And then I have the Fourier transform of that one, so it is h tilde of lambda inverse. Okay? I have alpha of lambda q minus 1 times x psi. Okay? I have d lambda, so it's d star lambda. It's not. It's a multiplicative. The star lambda. Okay, the star lambda, and then I have dx, but for x is in the fundamental domain, I shouldn't forget that. And I have also the psi, because I am applying the Parseval formula. Okay? I suppose this is clear. All right, so I can now go on, and I can define, in fact, a function. Okay, I mean, I can define a function g sub q, so that the expression which I am computing is really the following. You see, what I would like is that this expression now, that is the expression integral of h theta of lambda inverse over absolute of lambda and over rho. The rho is the usual rho, but for the ideal class group. What lambda range? Lambda range is in the ideal class group. Okay. No, lambda range is not in the ideal class group, in the ideal group, because it's h tilde. Okay. Okay. So lambda rank is in that group. Okay? So, okay? JS.
Yeah.
Okay. No, this is quite important. Now, as I said, the R measure on JS is like 1 over all d lambda around. Okay? Where d lambda is the additive R measure over lambda. So we have h tilde over h tilde of lambda inverse over lambdas. There is no problem there. Then we have alpha of lambda q minus 1 times x psi. Okay? And then we have d lambda, because I put this here. We have d psi, and we have dx. Okay? And then there was another one thing. Okay, x was belong to absolute of x was less than lambda, and absolute of psi was less than. Okay? Fine. All right. Fine. So you see that this expression, I can call it GQ at of x psi. Okay, because it is a Fourier transform, okay, of a certain function, which is appropriately defined. Now the function GQ I can name, and I can say that GQ of G, GQ at of x psi. So I group these two terms. I take this as my new variable of integration, so I call that U. If I call that V, I will call that V. So I have, if you want, equal to lambda Q is equal to 1 times V. Lambda inverse is equal to Q over 1 plus V. So GQ of V is equal to H tilde of Q over 1 plus V. I have to divide by absolute of lambda, which is the same as the absolute of multiplication by the absolute of lambda inverse, but absolute of Q is 1, so this is 1 of absolute of 1 plus V. And that's it. Okay? Now you see, what is using something extremely important, which is that precisely we are integrating on JS, not on Dirichlet. And we are extending the function h tilde, as before, to a function that is 0 elsewhere. And that's because it had compact support in JS. Okay? And that's because the measure theory was the same for JS as it was for Y. Okay? So now we are in business, we have this formula. Okay? But we are very far from home, extremely far, because there is a major difficulty at this point, which is that you see, now we can write the integral IQ as what? As the integral, multiple integral, where x is less or equal to lambda, x belongs to the fundamental domain. That's beautiful, that's fine. Where psi belongs to JS, but is no less than lambda. That's fine too. Not a problem with this. Yes, and then what do we have? We have JQ at of x psi. Okay. The d lambda is gone. And then we have dx d psi. Okay? Now we can do our usual trick, of course, which is changing variables here. And we're letting this variable u. Okay? This u will not be in the fundamental domain, because it's a product of x by psi. The x will be in the fundamental domain. And now we have a new pair of variables which are x and u. Okay? The dx d psi, as before, is equal to dx over absolute of x times du. There is no problem. Problem is not there. Absolutely not there. Okay? So we can do the Fubini. Okay, we can do the double integration by integrating first with respect to x and then with respect to u. There is no problem. This is entirely analogous to before. What do we know? We know that because dx over x with a factor rho is the multiplicative R measure of this star x, okay, on the Dirichlet group, and we are on the fundamental domain. Okay, we know that we have a very good computation for the integral for, if you want, so what would be the condition on x now, by changing variables? It would be that absolute of x, exactly as before, is last, and it's bigger than u over lambda. This is unchanged. There is no problem here. Okay? The x varies there in the fundamental domain. X is in the fundamental domain, and it varies here. Okay, so we can still integrate dx over x with a 1 over rho factor in this interval. It does give us what we want, namely 1/2. Sorry, it does give us, if you want, the integral for absolute of x between u over lambda and lambda of d star x, sorry, of dx over x, which is d star x, 1 over rho. That gives us 2 log prime lambda, okay, as before, 2 log prime lambda minus log of u. No problem, okay? This is no problem. So far, so good. So if you want, I can rewrite my integral in I sub q, okay, in a very nice way. We shall see where we go. So you see, we have a nice formula for I sub q, which is just parallel to what we were doing before. Okay? And which is that it is an integral for, again, for absolute of u less than lambda squared. It's the same story. Okay? So I sub q. Now remember that u varies everywhere. Okay? U is not in the fundamental domain because it was depending on the psi. Psi was spanning irreversible. So IQ is the integral for absolute of u less than lambda squared. Of what? Of 2 log prime lambda minus log u times g at k dq at of u d. Okay? No, x is in the fundamental domain. X is in the fundamental domain.
The change of variables from a C space.
The psi space. Okay, x remains where it stands. So x is in the fundamental domain. Otherwise, this would be divergent. This would not be finite. Okay? So x is still in the fundamental domain. U is not in the fundamental domain. Okay? So let me explain what is very hard here. It's that, you see, before it was a child game to say, well, we can replace this integral by an integral over all. Okay? I mean, all, no condition on lambda square.
Right.
And the remainder was easy to estimate. But here it's not the case, because we have a sum over q to perform. And we have to control the sum of the remainders in absolute value when we shall perform the sum over q. Okay? And that's real work. Okay? So somehow now what I will do, I will rewrite this in the following way. So I will define a function. See, I will define a function which is epsilon lambda of u, which is log of u, log of absolute of u, minus 2 log prime of lambda, and I will take the positive part, plus. By the positive part, I mean that this function is 0 when this function is negative, and that it is equal to this function when this function is positive. Okay? So you see that the first thing that you need to do, you absolutely need to control the convergence, I mean the individual term and their convergence in absolute value, but you need to control the following. The integral of g at q of u times epsilon lambda of u. Okay, we absolutely need to control these terms. Okay? And we need to control their sum. And to show that their sum is a big O of lambda to minus n for n. See, that's really where the main problem is. No simple argument can work. There is absolutely no simple argument that tells you that it's going to work. Okay. So let me explain how this works. Perhaps I should say in 2 words. I mean, why I mean, you get the wave formula if you know how to control this. I mean, this would be a little bit vague. Okay? So, why is it? So let's assume that we can do that. So what we shall have to prove is we shall have to control these terms and control their sum. Control the sum in absolute value of these terms. Show that it is absolutely convergent.
You're controlling the sum over Q, is that it?
The sum over Q. What I want is Q. I want to control the sum of absolute value of this over Q in the S unit. Okay, and I want to show that this is a big O of lambda from minus n.
These are like exponential sums. That's like the estimates and the exponential sums.
Right. Exactly.
These are just integers. Well, let's start on
No, because S might be contained not only the infinite place. I mean, S is a finite set of place. I mean, it includes the infinite place, but it can be there. So OS star can be quite a large thing. It's not a zero. It's like there's I rank in general, and the rank will grow. I mean, there's to be higher and higher. Okay, so I mean, what we have to do is to show that this is all of lambda's minus. Let me assume that and show you how we conclude. Okay, let me show you as a wave formula. So first of all, then we can replace this by an integral. Okay, where you have the 2 log rise lambda, of course. Okay, this will be the first term, and then you will have just g at q of u du. Okay, but now it will be no condition on u. Okay, now what is this equal to? Of course, there is 2 log prime lambda. Okay, now what is the integral of g at q of u in u? It is just g at gq of 0. Okay, times gq of 0. Okay, now what is gq of 0? If you follow the formula which is over there, okay, it should be equal, unless I made a mistake, to h tilde of q. Okay? Q or Q inverse, I don't care less. Okay? Now what is sigma of h tilde of q? It is h of 1. Okay? And there are only finitely non-zero terms in this sum because the q action is proper. And the support of h tilde was proper. Okay? So that's for one term. Now let's look at the more interesting term, which is here. Okay? Where is the miracle which transforms, as I said, the mass of a product into a sum? Well, it is simply the obvious thing that log of absolute infinity is the sum of the log of the user. Okay? So now, but this is a key point. As trivial as it looks, it is a very key point. Now, what does it mean? It means that now we have simply to look for each place B at the contribution of minus log of UB. Okay? But what is this? There is still a certain point. I mean, it still uses a Dirichlet thing. Maybe now we have integral, and now I don't have this. But I have minus log of UB. Okay? But look at this distribution, minus log of UV. It is a tensor product of the constant function 1 by a distribution only depending on the place B. Now the fact that there is a constant function 1 in front of g hat tells you that you restrict g hat to 0 for all the other places. Okay? Okay? So in fact you are evaluating g hat, q now, at a point which is 0, 0, 0, 0. Okay?
Just because of the structure of the distribution.
Just because of the structure of the distribution. Okay? Because it's independent of the other variables.
Oh, I see.
Okay? So it restricts to this. Okay? And moreover, at one place here, you put some free variable, I don't know, call it x, okay? And it performs the integral of dx over x, as usual, because this was the Fourier transform of this distribution. Okay? But now look at what is g hat q. And unless again I made a mistake, when I evaluate g hat q on 0, 0, 0, 0 and something, I have to add 1. So in fact I am evaluating it at 1, 1, 1, 1, 1, 1. Okay? Which is exactly the inclusion of the local field in the product. Okay? But moreover, I am making a sum over q. Now the Dirichlet theorem tells you that the local field k star b is discrete in the delta CS. Okay? And so it shows that only for finitely many translates of this, we intersect the support. of the function. So you also have only finite minimal zero. This is how we shall prove the convergence of the sum over I2. Because what we shall prove is that there are only finite minimal zero terms in the total integral, and the remainder is geometrically compatible. Okay? Okay. What is this group K star B is proper inside CS. Okay? Because the module, when you restrict it to the module is proper on CS, and when you restrict it to K star B, it's proper. But you see, if you have that situations where you have the two places together, and the reason why there are no two places together with each other is this formula. Okay? I mean, it's hidden behind this formula. Okay? Okay, I mean, that's really the key point. So now let me show how the estimate is done. So this. Okay, I'm not sure I want to treat this on I don't want to skip it. So I will begin it, but I don't want to skip it, so I will probably continue on it next time, because it requires work, and this work. I will just come to a nice formula. Okay, so let me explain how to rewrite these terms, and next time I will finish it. Okay, I don't want to just go there. Okay, so let me rewrite this in a nice way. Let's define a function psi of a variable by the following formula, that psi of lambda is equal to h of lambda inverse over absolute of lambda. Okay, and let us rewrite the g at q in this term. So remember that g at q of u was given by
It's on the top on the right.
here again. Yeah? Yes. So here, this is my function. Okay, h tilde. Okay, so in fact I can rewrite this as up to the row. I don't care about the row at this point because we checked the local case. So integral of psi lambda alpha of lambda q minus 1 times u. Okay, and then I have perhaps d lambda, and that's all. Okay, I think that's good. Yeah, everything is good. Okay. Now look at this formula. I mean, this formula is equal to alpha of minus u times what? Times the Fourier transform of xi, but evaluated where? Evaluated at q. No, QU, correct. Okay? Alpha minus u xi at q. Okay. So now if I make the product of epsilon, if I look at this sum here, the defect, delta lambda, okay, of q. Okay, this is my defect. What I want to control. It's equal to what? It's equal to the integral, remember, of g at q epsilon lambda of u. So in fact, it's integral of epsilon lambda of u, alpha of minus u, times xi at of qu du. Okay? Now, in this formula, I can make a change of variables. I can call qu equals v. This is dv, okay, because q has modulus 1. This is alpha of minus q inverse u. Okay? And this is epsilon lambda I claim of v, because epsilon lambda has a good taste to only depend upon the module. Okay? But what is this then? This integral? Yes, I mean, it is Fourier, again now, of what? Of the product of epsilon lambda by psi hat. In fact, it's Fourier inverse, because I have a minus here, and evaluated on Q inverse. Okay, that's my formula for delta lambda of Q. Okay? And now let me tell you, of course I will do it in detail, but let me tell you why we are done, essentially. We are done because these points Q inverse are proper. Okay? And this function is a Fourier inverse of a product of the function which is Lipschitz. I will prove it's Lipschitz, because the plus part taking the plus part is Lipschitz. Okay? And there will be absolute differential control on the operator of multiplication by epsilon naught. Okay? So, I mean, you know, it requires really some work. Of course, we shall do this work next time. And what we shall know then is that by the estimates that I had on the supernorm norm of the log Q and so on, we shall find that these numbers form a geometric series because of this. And that this geometric series is a big O of any inverse power. Then we shall do that. So next time is one day.